Hi everyone, thrilled to have you back with us at educator.com. This lesson we're going to go a little bit further with magnetism by talking about current carrying wires. Now our objectives are going to be to calculate the force on a current carrying wire in a uniform magnetic field, to indicate the direction of magnetic forces on a current carrying loop of wire in a magnetic field, to calculate the magnetic field produced by a current carrying wire, and to calculate the force of attraction or repulsion between two current carrying wires. So, let's start with the basic force on a current carrying wire. We know magnetic fields cause a force on moving charges, and current carrying wires are really just moving. Let's take a look here at a more detailed problem that'll bring us back to some fluids review as well. A U-shaped wire is placed in a tube and submerged in fresh water where there exists an 8 Tesla magnetic field into the plane of the page as shown. If the mass of the tube and wire is 1 kilogram and the volume of the submerged tube is 0.003 cubic meters, determine the current required to keep the system in static equilibrium. Alright, so we want that wire to stay right where it is. It's going to have a few forces acting on it. First thing is, let's figure out the direction of the magnetic force due to these different sections of wire. Over here on the right-hand side, as our current is going down, if I point the fingers of my right hand in that direction and bend them in the direction of the magnetic field, I get a magnetic force to the right. If I do the same thing over here on this side, this section of wire, I get a magnetic force to the left. Now, because we have the same current through both sections of wire, they're the same length in a uniform magnetic field, those two are going to cancel out. Force to the right, force to the left, exactly equal. We can ignore them. This section down here that's submerged, though, that's going to have a net magnetic field. I point the fingers of my right hand in the direction that that's going, bend them in the direction of the magnetic field, and I see that I'm going to have a magnetic force on that wire that's down. So when I draw my free body diagram for this situation, there's my wire. I have gravity pulling down the weight. I have the magnetic force, I'm going to write that as FB, but I also now have a buoyant force since it's submerged. And so I don't screw things up by writing FB again and getting confused. I'm just going to write that out as F buoyant up. And they all must match up for it to stay in equilibrium, for it to stay in the exact same position. Let's do our calculations now. The buoyant force must be equal to the weight plus the magnetic force on that wire. And the buoyant force, if you recall, is the density of our fluid times the volume of the fluid displaced times the acceleration due to gravity. That must be equal to mg plus the magnetic force, ILB sine theta, and in this case, sine theta again, sine 90 degrees is going to be 1, So the current, we'll solve for that. I must be rho Vg minus mg over Lb. So now I can substitute in my values to find that my current is going to be our density of fresh water, 1,000 kilograms per meter cubed. The volume displaced is given in the problem as 0.003 cubic meters. The acceleration due to gravity, 10 meters per second squared, minus our mass, 1 kilogram, times g, 10 meters per second squared, all over the length. The length we have is 1 meter, times the magnetic field strength, 8 Tesla. Plug that into my calculator and I come up with a current of 2.5 amps required to hold that in position in a static equilibrium state. All right, example 3, torque on a loop of wire. A loop of wire carrying current I is placed in the magnetic field. Determine the net torque around the axis of rotation here due to the current in the wire. Well, we've got some different sections of wire here. And just like before, we can see that as we look at this in the magnetic field, the sections that are going to make a difference here. Now let's call this section 1, we'll call this section 2. As we look at the current, as we're going to the left here toward the magnetic field, we're going in the opposite direction of the magnetic field. The current's in the exact opposite direction. We're not going to have any force. Here, as the current is traveling down, right hand in that direction, bend 90 degrees toward the magnetic field, I'm going to get a force that's coming out of the plane of the page. In this section at the bottom, we're lined up with the magnetic field. We're not crossing it. So we can't bend our fingers in the direction of the magnetic field. Or you could say the sine of the angle is 0. Sine theta, sine 0 is 0, so we get no magnetic force. But over here on the right, now we have current going up. We bend our fingers in the direction of the magnetic field, and I get a force that's going into the plane of the page. So there. What that's going to do is create a net torque. We're going out of the plane of the page on one side and into the plane of the page on the other. So let's find the magnitude of that. The force on this section of wire, section 1, let's call that F1, the magnetic force, is going to be ILB sine theta. Theta is 90 again, sine 91. So that's going to be, in this case, I times our height, h, times the magnetic field strength, B. And F2 is going to have the same magnitude, it's just coming out of the plane of the page. So that's IHB. Now to find our torque. Torque due to this section 1, well, that's force times the distance from our axis of rotation times the sine of the angle between those. In this case, our force is IHB, and our distance, well, if that whole thing is L, this is at L over 2 from that axis of rotation. Our torque from section 2 of the wire over here also again has the same magnitude, IHB L over 2. So our net torque, which is just torque 1 plus torque 2, IHB L over 2 plus IHB L over 2, is just going to be IHB times L. So by running current through this loop of wire in a constant magnetic field, you can create a torque that's going to cause it to rotate, an electric motor. Magnetic field due to current carrying wire. Moving charges create magnetic fields, and wires carry moving charges, so you must have a magnetic field around a current carrying wire. The magnitude of that magnetic field created by a current carrying wire is given by this formula. B equals mu naught, the permeability of free space, times the current flow in amps divided by 2 pi times the distance from the center of that wire. The direction again is given by a right-hand rule, but it's another right-hand rule now. Point your thumb in the direction of the current flow. Let's assume this is our wire. If I point my thumb in the direction of current flow, if the current is flowing up, as I wrap my hand around the wire, that's the direction of the magnetic field. I'm going to get a circular magnetic field around the wire. It's stronger closer to the wire, weaker the further away you get, related to 1 over r. And the direction, whether it's clockwise or counterclockwise, you use that right-hand rule. Point your thumb in the direction of positive current flow and wrap your fingers around. That's going to show you the direction of the current flow around that wire. So for example, down here in the bottom left, if the current is coming out of the plane of the page or out of the screen toward you, point your thumb in that direction, wrap your fingers around it, and you should see that you get a counterclockwise rotation as your fingers move forward. Going into the plane of the page or into the plane of the screen, however, if the current going away from you, wrap your fingers that way, you should see a clockwise direction for the magnetic field. And over here on the right, we're just showing that same thing from a side view. If the current is going sideways, point your thumb of your right hand in the direction of the positive current flow. Above the wire, it's going to be coming out toward you. Fingers in the direction of current flow around the solenoid, and your thumb will point to the north pole of your electromagnet. So for example, if I have the wire wrapping around this way, if I take the fingers of my right hand and wrap it in that direction around the wire, my thumb points to what's going to be the magnetic north of my electromagnet. Another right hand rule. By the way, if inside this solenoid I place something like an iron bar inside it, it's going to get much, much, much stronger. So that electromagnet, if you put something like iron inside it, gets much stronger, a way to greatly increase your magnetic field strength. Now, let's talk about forces on parallel wires. Current-carrying parallel wires exert forces on each other. Why do they do that? Well, if you have two wires that are parallel to each other, the current through one wire is going to create a magnetic field. We just determined that. Now, the other wire has moving charges. Moving charges going through a magnetic field observe a force. So they're going to create a force on each other. So a typical sort of AP question might be something like, if we have a wire with current flowing that way and another wire right beside it with current flowing toward it, what are you going to see for a force between these? Which direction? The way I like to think about it is, let's start with this one on the left. If we have a current flowing this way, if we think about the direction of the magnetic field, do the right-hand rule, I'm going to have the magnetic field coming toward me on this side, and as it comes around, it's going to be going into the plane over here. Now, the current here, I can use another right-hand rule. Positive current, point my fingers up in this direction, bend in the direction of the magnetic field due to the other one, and I'm going to see a force to the left on that wire. Now try the same thing in the opposite direction to prove that you're going to see a force on that original wire back toward the middle. So if we have current flowing in the same direction, we get an attractive force. On the other hand, if we have two wires where the current is flowing in opposite directions, you're going to see that they have a repulsive force. They're going to force each other away. Try proving that. A really great way to practice making sure you understand how some of those right-hand rules work. Let's take a look at the magnetic field due to two wires. Two different wires carry current as shown below. Find the magnetic field here at point P in between them. Well, let's call this, on the left, current 1, wire 1, and on the right, let's call that wire 2. The way we're going to find the net magnetic field at P is let's find the magnetic field due to I1 first, then we'll find the magnetic field due to I2, and we'll add them together. So the magnetic field due to 1 is going to be mu naught I over 2 pi r, which is 4 pi times 10 to the minus 7 times our current, 4 amps, over 2 pi, and the distance from our wire to point P is 0.15 meters. When I do that, I'm going to find that B1 is equal to about 5.33 times 10 to the minus 6 Tesla. All right, in the direction by the right-hand rule, point my thumb in the direction of positive current flow, wrap my fingers around, I'm going to see that that is going to be into the page at that point. Now let's do the magnetic field strength due to wire 2. V2 is also mu naught I over 2 pi r, or 4 pi times 10 to the minus 7 times 3 amps over 2 pi, and our radius now, our distance from the wire, 0.1 meter. So when I put that in my calculator, I find that B2 is about 6 times 10 to the minus 6 Tesla. As far as direction goes, let's do the right-hand rule again. Point the thumb of my right hand in the direction of positive current flow, wrap around that imaginary wire, and I see that that's going to be coming out of the plane of the page. So that's going to be going in this direction. They're in opposite directions. So if I want the total magnetic field strength at point P, that's going to be equal to the magnetic field strength due to 1 plus the magnetic field strength due to 2, which is going to be equal to, well, B1 was 5.33 times 10 to the minus 6 Tesla, and that's coming out of the page. And we also have this 6 times 10 to the minus 6 Tesla, or that's going into the page. 6 times 10 to the minus 6 from B2 is coming out of the page toward me. Well, notice out of the page is stronger, so I'm going to subtract them, negative 5.33 times 10 to the minus 6 plus 6 times 10 to the minus 6, to give me a total of about 6.7 times 10 to the minus 7 Tesla. And because out of the page is stronger, the net magnetic field must be out of the page. So there's my answer. The magnetic field at point P, 6.7 times 10 to the minus 7 Tesla, out of the page. All right, let's take a look at a problem with the strength of an electromagnet. We've got a solenoid of length 10 centimeters containing 150 coils of wire and carrying a current of 10 milliamps. Determine the magnitude of the magnetic field created inside the solenoid. Well, the magnetic field strength due to a solenoid is mu naught times N times I, where N is the number of coils per unit length. So that's going to be 4 pi times 10 to the minus 7 mu naught times, we have 150 coils over 0.1 meters, times our current flow, 10 milliamps is 0.01 amps. So I would get a magnetic field strength of about 1.88 times 10 to the minus 5 Tesla. All right, let's do an example with the force on a wire. We've got a 5-meter long straight wire, so L equals 5 meters, which runs at a 45-degree angle, theta equals 45 degrees, to a uniform magnetic field of 5 Tesla. B equals 5 Tesla. If the force on the wire is 1 Newton, F is 1 Newton, find the current I in the wire. All right. The force on the wire, FB, is equal to ILB sine theta. We're looking for current, therefore current is going to be the force over LB sine theta, which is going to be 1 Newton over, we've got 5 meters, our 5 Tesla field, and the sine of 45 degrees, which is going to be square root of 2 over 2. Therefore, our current is about 0.0566 amps, or 56.6 milliamps. One more problem. Determine the direction of the force on the 2 current-carrying wires shown below. Well, this comes straight from our previous slide where we were talking about what the force is between 2 current-carrying wires, parallel wires, whether if the current's in the same direction or opposite directions. And you can figure this out by working through the right-hand rules, or remembering that in opposite directions you have a repulsive force between them. All right, hopefully that gets you a good start on magnetism as it relates to current-carrying wires. Thanks so much for your time and for visiting us at educator.com. Make it a great day, everyone.